for Science Salah Lotfy channel. In today's episode, we will continue our exploration of the ongoing events in Lebanon, but from a new perspective. While we previously discussed hardware vulnerabilities, we now turn our attention to advanced methods used to detect explosive materials such as TNT and C4. These methods are crucial for ensuring public safety and preventing potential threats. Scientists in high-tech laboratories are constantly developing and refining techniques to identify these dangerous substances. From sophisticated sensors to chemical analysis, the technology used is both cutting-edge and highly effective. By understanding the properties of explosive materials, researchers can create more accurate detection systems. This not only helps in thwarting terrorist activities, but also aids in forensic investigations, providing critical evidence in criminal cases. We are excited to present a cutting-edge research paper titled Air Cargo Inspection using Pulsed Fast Neutron Analysis. This groundbreaking study delves into innovative methods for enhancing the safety and security of air cargo. By employing advanced neutron analysis techniques, the researchers have opened new avenues for detecting hazardous materials with unprecedented accuracy. The paper is authored by Strellis, Gozani, and J. Stevenson from Rapiscan Laboratories, Sunnyvale, California, USA. These esteemed scientists have dedicated years to perfecting this technology, which promises to revolutionize the way we approach air cargo inspection. Their collaborative efforts have resulted in a comprehensive study that not only highlights the technical aspects, but also the practical applications of their findings. This study sheds light on how fast neutrons can be used to identify and analyze potentially dangerous substances. By utilizing pulsed fast neutron analysis, the researchers have demonstrated a method that is both efficient and reliable. This technique allows for the rapid scanning of cargo, ensuring that any threats are detected swiftly and accurately. The implications of this research are vast, offering significant improvements in both safety and efficiency. The study offers a critical tool in the fight against terrorism. With the ever-present threat of dangerous materials being smuggled through air cargo, this research provides a much-needed solution. The advanced technology described in the paper can be integrated into existing security protocols, enhancing the ability of security personnel to detect and neutralize threats. This not only protects lives, but also ensures the smooth operation of global air transport. We would like to extend our deepest gratitude to Professor Dr. Tarek Nagla, a distinguished expert in the field of nuclear and radiation engineering. His unwavering dedication and profound knowledge have been instrumental in advancing our understanding of complex scientific phenomena. As the main supporter of our channel, Professor Nagla has provided invaluable insights and resources that have significantly enriched our content. His commitment to fostering a culture of scientific inquiry and innovation is truly inspiring. His continued contributions allow us to dive deeper into such critical topics, enabling us to explore and present cutting-edge research findings to our audience. We are immensely grateful for his support, which empowers us to bring you high-quality, informative content. By examining these topics from various angles, we aim to provide a comprehensive understanding of the latest advancements in science and technology. Thank you, Professor Nagla, for your unwavering support and dedication to the pursuit of knowledge. Stay tuned as we explore the application of this groundbreaking technology and its relevance to the current situation in Lebanon.
Now let's dive into the first part of this fascinating research on air cargo inspection using Pulsed Fast Neutron Analysis, PFNA technology. The research, developed by Strellis, Gozani, and J. Stevenson from Rapiscan Laboratories, introduces an advanced system that is already operational at the George Bush Intercontinental Airport in Houston, Texas. This system was funded by the Transportation Security Administration, TSA, under the Department of Homeland Security, DHS, to enhance aviation security by detecting explosives in cargo. The system is designed around a powerful Van de Graaff accelerator, operating at 3.5 MHz, which produces deuteron pulses with a full width at half maximum, FWHM, of 1.5 nanoseconds. These deuterons collide with deuterium gas to generate neutrons at an energy of 8.5 mega-electron volts, MeV, with a beam intensity reaching up to 140 microamperes. A neutron collimator focuses the beam, creating a spot approximately 9 centimeters wide and 12 centimeters tall at the center of the cargo container. But how does this system actually detect explosives? It's all about gamma rays. When these fast neutrons interact with the cargo contents, they cause inelastic scattering reactions, which produce gamma rays. Surrounding the inspection volume is an array of sodium iodide (NaI) detectors, each 15.25 centimeters in diameter. These detectors collect the gamma rays emitted by the cargo, allowing the system to analyze the elemental composition of the materials inside. By using a time-of-flight technique, the system can determine the precise location of the inelastic neutron scattering reactions, producing a three-dimensional image of the cargo. This image has a granularity of approximately 6.3 by 6.3 by 8 centimeters, which is precise enough to detect the presence of dangerous substances like TNT or C4. What's truly revolutionary about PFNA is that it doesn't rely on traditional methods like particulate detection or radiographic imaging. Instead, it focuses on measuring the elemental composition of the cargo, identifying specific signatures, such as the 4.44 MeV gamma ray from carbon, the 6.13 MeV gamma ray from oxygen, and gamma rays from nitrogen. This approach gives the system a unique advantage in detecting explosives, making it far more effective than conventional technologies currently used for air cargo screening. In the next section, we will explore the specific measurements and the real-world application of this technology.
Let's now explore the technical approach behind the Pulsed Fast Neutron Analysis, or PFNA, system, and how it creates a three-dimensional elemental image of the cargo's contents. The PFNA system uses a method called time of flight, or TOF, combined with gamma-ray energy spectral measurement to analyze the entire volume of a cargo container. The key here is the ability to detect the precise three-dimensional position of any potential threats within the cargo by measuring the gamma rays emitted during neutron interactions. The process begins with a deuteron beam hitting a deuterium gas target, producing neutrons through a reaction known as D plus D 3 Chi plus NN. These neutrons are produced at around 8.5 MeV, allowing them to penetrate deep into cargo. This energy ensures effective interaction with materials inside the container. When neutrons bombard the cargo, they interact with atomic nuclei, triggering inelastic scattering reactions. The interaction leaves the nuclei in an excited state, and as they return to their ground state, they emit gamma rays. The gamma rays detected by the PFNA system reveal the elemental composition of the cargo, identifying potential threats. The system measures gamma rays from key elements like carbon, oxygen, and nitrogen, indicators of explosives. These gamma ray signatures help the PFNA system differentiate between dangerous and non-dangerous materials. Now, let's dive into the PFNA system setup. The system uses a Van de Graaff accelerator to generate deuteron beams with a pulsing frequency of 3.5 MHz and a pulse width of 1.5 nanoseconds. This creates neutron pulses to measure the timing and energy of gamma rays emitted by the cargo. As the beam travels, it passes through several components, including a quadrupole triplet lens, which focuses the beam before it strikes the deuterium target to create neutrons. These neutrons are then directed into the cargo container by a moving scan arm, which allows the beam to scan the entire volume of the container. The PFNA system also incorporates two types of detectors: large NI detectors to measure the gamma rays and plastic scintillator detectors for radiographic imaging. Together, these detectors create dual-species radiography, capturing both neutron and gamma ray images of the cargo. This helps further refine the system's ability to detect dangerous substances by analyzing the elemental densities and ensuring the most accurate threat detection possible. In the next section, we will look at the results of real-world tests using this technology and how it has proven effective in identifying explosives like TNT.
Let's now look at how the Pulsed Fast Neutron Analysis, or PFNA system, detects threats like TNT in air cargo using gamma ray spectra. When a neutron interacts with a target, such as a TNT explosive, gamma rays are emitted at specific energy levels, which help identify elements like carbon, oxygen, and nitrogen. For instance, nitrogen emits gamma rays at 1.63 MeV, 2.31 MeV, and 5.11 MeV, while oxygen emits at 6.13 MeV. This precise data helps us understand the elemental composition of any potential threats hidden in cargo containers. The PFNA system uses time-of-flight measurements to detect these gamma rays. TOF works by calculating the time it takes for the neutron to reach the object and produce gamma rays, and the time it takes for the gamma rays to be detected. This is done using a time-to-amplitude converter, or TAC, that starts when the neutron pulse is produced and stops when the gamma ray is detected. The difference in time gives us important information about the material in question. Now let's talk about how the PFNA system analyzes these measurements. The data is collected in a two-dimensional histogram, where the gamma ray energy is on the horizontal axis and the time of flight is on the vertical axis. This histogram allows the system to isolate specific elements. For example, in Figure 7 of the research, we see the gamma ray peaks from carbon, oxygen, and nitrogen, which are critical in identifying explosives like C4. By analyzing these gamma ray peaks, the system can create three-dimensional images of the cargo, highlighting areas that contain dangerous materials. In Figure 8, you can see an image of TNT simulants hidden in an air cargo container. This image was produced by the PFNA system, which identified the oxygen levels within the container and flagged them as potential threats. The system divides the container into small sections called voxels and evaluates the elemental composition of each voxel. If the system detects a composition similar to explosives, it triggers an alarm and displays the location of the threat in 3 dimensions. What makes PFNA truly unique is its ability to analyze not just the density, but the actual elemental composition of objects. Unlike traditional X-ray systems, which can only detect unusual densities, PFNA can automatically detect materials that differ in elemental composition, such as explosives, narcotics, and other hazardous substances. In conclusion, PFNA's three-dimensional imaging and ability to identify specific elements make it an essential tool in modern security applications. Its use in air cargo inspection has already shown promising results, with the ability to scan between 9 to 12 LD3 containers per hour, making it both efficient and effective. Stay tuned for the next section, where we'll dive deeper into the real-world impact of PFNA technology. Ready to dive into the future of air cargo safety? Let's break it down. Air cargo transportation is the backbone of global trade, but with great power comes great responsibility. Ensuring the safety and security of our air cargo is paramount. In the past, traditional methods like X-rays and physical inspections were the norm. But now, we're stepping into a new era thanks to innovative technologies. One of the game changers in this field is Pulsed Fast Neutron Analysis, or PFNA. This technology is designed to detect hidden threats with high precision, making air cargo inspections faster and more reliable. PFNA works by bombarding cargo with fast neutrons. When these neutrons interact with the materials inside the cargo, they emit gamma rays. These gamma rays are then analyzed to determine the composition of the cargo, identifying any potential threats. What's incredible is that PFNA can detect threats that traditional X-ray methods might miss. Another breakthrough is the use of advanced AI algorithms to analyze data from cargo scans. AI can process vast amounts of information quickly and accurately, flagging any anomalies that might indicate a threat. This not only enhances security but also speeds up the inspection process, reducing delays and improving efficiency. But technology isn't just about detecting threats, it's also about ensuring the smooth flow of goods. Innovations in smart sensors and IoT devices are making it possible to monitor the condition of cargo in real time. This means that temperature-sensitive goods like pharmaceuticals and perishables can be tracked and maintained at optimal conditions throughout their journey. Before we wrap up, I'd like to express my deep gratitude to the researchers behind this remarkable work: D. Strellis, T. Gozani, and J. Stevenson, from Rapiscan Laboratories in Sunnyvale, California, USA. Their research on air cargo inspection using Pulsed Fast Neutron Analysis has been instrumental in advancing our understanding of threat detection technologies. I also extend a special thank you to Professor Dr. Tarek Nagla, our main supporter, for providing this research to the For Science Salah Lotfy channel. His dedication has allowed us to explore scientific topics and connect them with real-world events, such as the current situation in Lebanon. By studying and presenting research related to on-the-ground events, I aim to offer you a scientific perspective on today's pressing issues. Thank you for watching, and stay tuned.